Okay, welcome to the second session. I'm Nicola Cesabianchi. I'll be chairing this session. It's a long one, so be prepared. So the first speaker is Rishabh, Dudeja, and Daniel Su, and the title is Learning Single Index Models in Gaussian Space. Rishabh?
Hi, so I'm going to talk about learning single index models in Gaussian space. This is joint work with Daniel Su. So the setup is as follows. We are given n observations, each consisting of a covariate, which is p-dimensional, and a response y, which is a real-valued response, which are generated IID from the following model. First, we sample the covariate x from a p-variate Gaussian distribution. Then the response y is sampled such that the conditional mean of the response given the covariate is some function of the covariate. However, this function has a low-dimensional structure. In particular, it depends on the covariate x only through the projection of x on a low-dimensional subspace U star. The dimension of U star is k, and it's called the index space. When k equals 1, this model is called a single index model, and U star can be generated by a single vector, little u star, and little u star is called the index vector. When k is more than 1, this model is called the multi-index model. The function g is called the link function, and it's assumed to be unknown. And the goal is to estimate the subspace U star. Why is this problem interesting? This problem generalizes some well-known problems like the phase retrieval and one-bit compressed sensing problem. Both these problems are single index models. In phase retrieval, the link function g of z is z square. And in one-bit sensing, the link function is the sine function. However, because we model the link function as unknown, any estimators that we come up for learning single index models actually work for these problems too, with the additional advantage that they have robustness to misspecified link functions. Okay, so the overview of what we did in this work is as follows. We analyze the population landscape of a natural objective and show that it has benign structure. The objective suggests a natural iterative procedure to learn single index models, and this procedure has sample complexity, which is polynomial in the ambient dimension p. Okay, so before I get into the details of the procedure, I need to introduce some notation. It's going to be extremely convenient to expand the unknown link function in terms of the Hermite polynomials. We denote the Hermite polynomials with hi. Hi is the ith Hermite polynomial, which we also call the ith harmonic. So in the single index case, where the unknown link function is a univariate function, we can write it as a linear combination of these Hermite polynomials, and the coefficients ai star, which appear in this linear combination, are going to be particularly important for us since they show up in our sample complexity bounds. When k is more than 1 and we are in the multi-index case, we can again write an expansion of this form, except with tensor product Hermite polynomials. Okay, so so we study the following objective. This objective is actually a family of objectives indexed by the harmonic L. And so basically what this objective FL does is that it tries to use the energy present in harmonic L to extract information about the index vectors. And intuitively what it does is that it tries to orient its argument U such that the empirical correlation between the responses and the Lth Hermite polynomial is extremized. So our first result is about the population landscape of this objective FL. It says that it has a benign structure. So for any local maximizer with a strictly positive expected objective value, the maximizer is actually contained in the index space U star. And for any local minimizer with a strictly negative expected objective value is also contained in the index space U star. So when we're in the single index case and k equals 1, the objective has a particularly nice form. It is just the inner product between the argument of the objective and the index vector U star to the power L. But this also tells us that as soon as L is more than 2, this objective is not a strict saddle objective, which means that there exist points, namely all points which are orthogonal to the index space, at which both the gradient and the Hessian of this objective is 0. And so general analysis for gradient descent for strict saddle problems don't apply. Okay, so the population result actually suggests a simple objective to a simple algorithm to learn index models, and so the algorithm takes in a harmonic L. It'll use the information present in harmonic L to learn the index vectors. So first, it initializes randomly on the unit sphere. Then it evaluates the gradient of the objective FL at the random initialization and rescales it so that it has unit norm. And then it repeats this step once more, and then it returns the resulting vector as its output. When we run this algorithm on the first or the second harmonic, this algorithm actually corresponds to previously known estimators called the average derivative estimator and the principal Hessian's directions estimator. Both of these estimators have been used to design estimators for the one-bit sensing problem and the phase retrieval problem. However, because now we are assuming the index function is unknown and arbitrary, we pick L using a cross-validation type of procedure. Okay, so here's the first result about the performance of algorithm 1. So it says that suppose the data was generated from a single index model and we run the algorithm 1 on harmonic L. Then its output u hat has the property that the dot product between u hat and the index vector u star is 1 minus an error term. This error term scales as root p over n, which is the dependence on p is expected because we are now estimating a p-dimensional object, namely the index vector. It also scales inversely with the energy present in the harmonic L, which appears in the form of the coefficient AL star. Okay, however, this result holds only if we are given an initial number of samples which exceeds p to the L. And this initial number of samples is required to make sure that random initialization works. Okay, so now we can apply algorithm 1 and its analysis to learn index models where we assume the link function is unknown, which are called semi-parametric index models. Existing work often makes assumptions on link functions which seem ad hoc. We make more standard assumptions on the link functions. In particular, we assume that the link function g is smooth, that the second moment of the second derivative is bounded by a constant r square. We also make a minimum signal strength assumption which says that the second moment of the first second moment of the first derivative is lower bounded by a fixed constant mu. And to see why like this minimum signal strength assumption is required is it's important to note that if this second moment of the first derivative was exactly 0, then the first derivative is exactly 0, and the link function does not depend on some of its coordinates, and so there's no hope of estimating the index vectors that feed into those coordinates. Okay, so here's the result for learning single index models. So it says that essentially algorithm 1 outputs a vector which makes whose dot product with u star is at least 1 minus epsilon, and it requires samples which is p over epsilon square, which is the cost of estimating a p-dimensional vector, and an initial number of p to the a polynomial in p number of samples, and the degree of the polynomial depends on the smoothness and the minimum signal strength assumptions. And essentially the same algorithm is guaranteed to return a vector which is epsilon close to being in the index space with again a similar sample complexity when given data generated from a multi-index model. So the main question for future work is that whether dependence on dimension can be made linear without compromising on computational complexity. And the main bottleneck is that it seems hard to extract information from harmonics bigger than 3 in order p samples. Okay, thank you.
Are there any questions? Yes.
Because we assume that the covariance, the covariates are Gaussian distributed, the Hermite polynomials are suited for the Gaussian measure. So that's why, yeah.
Okay, let's thank again the speaker. And